It's been almost 2 years since I last uploaded the video on this channel. It has been a turbulent time, things change, and so have I.
So for me, the whole interest is almost everyone who's developing is developing in one of the top 5 or 6 languages.
Yeah.
And all of those languages from a sufficient distance are exactly the same. They're different syntactically, they might have slightly different set of constructs, but they're all more or less exactly the same language. It doesn't matter whether you're using JavaScript or C# or Swift. There are advantages and disadvantages to each of those, and there are contexts where they're better or worse, but they're all the same language. And the problem with that is it doesn't give us enough breadth and enough opportunity to explore the ways that you could compute. And most of the time that's okay, because the kind of apps that we're putting together can be built relatively easily in these languages. But sometimes the code is just a nightmare because the language isn't really designed for it. And so if people weren't willing to explore different ways of thinking about the fundamental problem of computation, then we would never have had functional programming, for example, because we would have just gone with imperative and we wouldn't have had OO or anything like this. So my view is that I should be continuing to think about all of these different ways in which we can compute. And why would I do it in a boring way? Why wouldn't I do it in an interesting way? So one of the issues that I looked at a few years ago now was practically every language that everyone ever uses, the word order is absolutely critical. If you get a word out of place within the program stops working. The compiler won't even accept it. And I spent a lot of years teaching first-year university students how to program, and they spent most of their time getting at least one word out of the right order. So I looked at this and I thought, is it possible to have a programming language where the word order isn't actually important, where somehow you mark what each component of the program is supposed to be doing in an individual statement? I mean, is it the assignment object, or is it the data that's being assigned, or is it in fact the assignment operator itself? And it turns out, yes, you can write a language like this, and so that it wasn't going to be boring to me, I decided, well, I'm going to do that as Latin, because Latin works that way. You mark each component of a sentence, so each word in the sentence has a marker on it, which in the case of Latin is a suffix, and that tells you what that word is doing in the sentence. So there are plenty of languages, especially European languages, that have that same kind of inflected characteristic, or at least the remnants of it, because they have this influence of Latin. But I thought, well, most programming languages are basically written in English. The keywords are English, and even some of the ideas are English, of the grammar. So why don't we see if we can do something different? And that's what I did. I did that with Latin. If you look at older programming languages like PostScript, for example, well, PostScript has a very different worldview on how you are going to do computation. You know, most people think it's only for running printers, but no, it's a full programming language. It's based around a stack model rather than a general data model. So naturally, because of that, then it's reverse Polish notation. The verbs all come at the end. It doesn't have variables in the normal sort of way. You don't need them because you just redesign a subroutine to return a different value, and that's morally the same thing as assigning to a variable and then getting the value back from the variable. So this is what I was doing last year. I was just exploring these different kinds of approaches to programming, just to see what we could learn from it, just to sort of expand my brain and hopefully expand the brains of the people who listen to the talk.
One thing that I wanted to drop in here is a few years back I heard a talk by Bob Martin, and he said that basically the talk was all about the lost programming language, because he claims that now we have tried everything and now we know what's good in a language and what's bad in a language. So now it's time that we finally settle on a single language. And he comes to the conclusion that it should be Clojure.
Well, what a surprise there. Well, I mean...
you are the exact opposite here. You say
I am.
We should still explore stuff because we are not exploring enough.
It was very brave of Bob to do that. I don't know whether he was doing it slightly tongue-in-cheek even, because
no,
the history of science and engineering and every technical discipline is littered with the corpses of very senior and famous people who proudly announced, we have now reached the end of all innovation.
Yeah.
And it is just not the case. It is never the case. It will never be the case. And so anyone who tells me, well, we can stop now because we have everything perfect, they would have been telling me that 20 years ago about, I don't know, C++. Or they would have been telling me that 40 years ago about one of the modern versions of Fortran. And it's simply not true. And it's not true today. It's harder to see that it's not true because there are so many more languages. So much more of that idea space is being explored in one way or the other. But I think that statement is simply a failure of imagination. That it's always possible to come up with new ways of thinking about programming. I'm a reasonably clever guy, but I'm not even in the top 10 clever guys that I know. And I personally have come up with 5 or 6 different ways of computation. Now, it's not necessary that any of those is actually usable or practical, although several of them have found their ways into mainstream programming languages. And if I, as just a regular guy, can do that, then really, really clever people, really good language designers, ought to be able to come up with dozens of them, each one of them. So the idea that we've now reached the apex of all possible language design strikes me as being extremely unlikely. Let's just say that. And one thing that I noticed this year, because last year the things that you showed were actually implemented in real life, and I could imagine that it's happening in the background. The Latin compiler was clearly something that should work. But this year you came up with something less likely that it's real. So tell me about that. So you want the scoop on that? You want the inside story of that?
Yeah.
That is true. The quantum superposition stuff is feasible. There are quantum computers that can do many of the things that I talked about. And the particular constructs that I talked about in that part of the talk have been built into at least the Perl 6 programming language. Now, of course, obviously, Perl 6 is not running on quantum computers yet.
But it could.
But it could. And the point is that these concepts still work even if you can't take advantage of the massive parallelism of quantum computation, because you can take advantage of the massive parallelism of other kinds of massive parallelism. You can do it with threading, you can do it with processors, you can do it in all kinds of ways, and that's what Perl 6 does.
Okay.
For the other techniques that I talked about in that talk, the zero-time computation,
which actually needs 10 suns and stretching out,
which needs a ridiculous amount of hardware that we're never going to be able to create. Well, I shouldn't say we're never going to be able to create it, because then I'm committing the same sin as everyone else. It's unlikely that in the near future we will be able to extrude the mass of 10 suns into a neutronium spindle, which we can then navigate. But the concept of that was just a way of me building an API that allowed me to do other things. And in that particular case, yes, I was clearly cheating there. And in fact, the cheating that I was doing there was that I was just doing auto-memoization of functions. And that's all that the thing was doing. But the last one that I talked about, the running things backwards and forwards in time, of having variables that run backwards and forwards in time, yeah, that's never going to happen. But the software that I was demonstrating was actually doing that in simulation.
Okay.
What the code actually did was it took the code that I had written and it ran it forwards through the program, getting a result, but it tracked every one of the variables in the program. It tracked its entire state history through the entire run of the program. And again, in Perl, that's something that's really easy to do. It's very easy to create a variable that is in fact a wrapper around an object, and that object can just remember every value that it was given, and it can remember at what line in the code and what statement in the code was it given that value. And then what my simulation did was it took each statement in that program and ran it in reverse. It ran them in the opposite order, and when it was asked for the value of the variable, it just consulted the previous value of the variable from its own timeline. And so it ran backwards in time, and then when it got to the beginning of the program, I ran it forward in time with the new timeline of values.
Okay.
And all I'm doing is I'm tracking those timelines running through the program in forward and reverse direction alternately, and I just watch them and wait until they converge to a consistent Feynman diagram, basically. And as soon as that happens, I run the thing one last time with the converged values, and that computes the result.
Okay.
So obviously, all that was a way of doing was writing iterative algorithms. And if you think about the examples that I showed basically Newton's method for finding square roots, and I showed binary chop, and both of those are iterative convergent mechanisms. And all the examples that I showed there were iterative convergent mechanisms. And that's all I was doing. I just created maybe not an easy API, but a straightforward API for writing iterated convergent algorithms without having to use loops in the normal way. So the advantage I get out of that is that it lets me think about these kinds of algorithms in an entirely different way. And that was the goal. But as I said at the time, every single piece of code that I demonstrated during that talk was actually running live. And all of it was in some way or another simulating precisely the physics that I had promised. Yeah. But of course, it was the reason that I can get away with that is that I was doing small enough calculations that you couldn't tell that it wasn't, in fact, running in negative time. If, for example, with the prime number tester, for example, if I had taken that out to 100 million, then it would still see the slowdown. Eventually. So there was a trick there. Obviously, there was a trick, but part of what I also try and do is in my talks leave people with a sense of wonder. Leave people with a sense of the world is bigger and stranger than I had expected it to be.
As I said, I have changed a lot, and so with this channel. It's going to be a bit more hands-on, so check back on this channel for more content soon.